Okay, this is a long one here. We're on part D, I think. I'm going to wrap this up here. So, parasites can also change ecological communities. We kind of alluded to some of this earlier. We'll have a couple examples here, but by reducing host performance and growth rates, parasites can change the outcomes of species interactions, community compositions, and even the physical environment. This is an example where you've got two flower beetles with no parasites. The I hate colors. I don't know, orange one. Castaneum has a competitive advantage. So on a level playing field, Castaneum will outcompete. It looks like confusion. Yeah, maybe. Confusum. So, Castaneum and Confusum. So Castaneum in a level playing field with no parasites outcompetes Confusum. With parasites, they have a percentage of wins. Okay, so this is it's funny. In a system where there's parasites, Castaneum loses or is less, has a lower competitive advantage compared to Confusum. So they both, it's interesting where there's a differential impact of these parasites, where one will be weakened more by the parasites compared to the other species. And parasites can alter the outcome of predator-prey interactions by decreasing the physical condition of infected individuals. And this can go either way. So typically think about it like as if the prey is parasitized, it's going to have a slight, parasites are taking energy. So because the prey, which is a host to a parasite, is having energy taken, or perhaps pain generated or some other malady by the parasite, it's going to be a little less responsive, a little less sharp, a little tire out more easily, not be as fast as it normally would, and that gives the predator just slightly more advantage to go after the prey. And that'll increase the predator's chance of catching that prey because it has a parasite. Now, the opposite could be true in that the parasite could be in the predator, and that'll slow the predator down and reduce its chances of catching a prey. And these are, often I would argue part of the hidden dynamic of ecology, meaning we know that wolves eat elk, but how are they selecting which individual elk to eat? There's been a lot of recent work looking at, joints or other sort of like maladies that the elk have that at first glance we don't detect, but then they look at the kill and of the wolves in the Greater Yellowstone and see, well, they actually had a bad knee that we couldn't tell by their gait, but those could detect there's something slightly off by the individual. Same thing could be true for parasites. It's not obviously like the prey aren't visibly struggling, but they're just slightly off edge, and that's all the predator needs is just a slight edge to be able to capture that prey. So these probably have a much bigger impact on ecology than we can understand. It's just a really hard thing to measure. You have to have parasite load data for a whole bunch of different organisms and to compare, or members of that population, and figure out how that relates to who gets eaten. And parasites can also change the behavior of the host, like the protozoan we talked about with the cats. I want to go back to the name of that one because I forgot it. Where is it? Ectoparasites, endoparasites. It's like plasmosis, something plasmosis. Is it right at the top? Where did that one go? Plasma didn't. No, it was plasma. It was right. It was. Oh yeah. Toxoplasm. Gondii, yeah, toxoplasm. I just wanted to remember the name of toxoplasm because it's this one that changes the behavior of the rats to make them less wary of cats. And as I mentioned, toxoplasm is prevalent in 70. Let me look it up. That's a hint. Let me look it up. Okay, yeah, I wanted to look that up because I was going to put that on the exam next week. So toxoplasm gondii is estimated to be in 30 to 70% of the U.S. population. It's the same genus and species that makes rats less wary of cats. So therefore, the rats are more likely to be eaten by the cats, and then the host can transfer to the cats. And toxoplasm gondii, Gondii, Gondii. I suck at Latin names. So toxoplasm gondii, 30 to 70% of the worldwide population. It's a massive infection rate. 30 to 70% of the worldwide population. Arguably affects, arguably not. It's a bit of a gray area. I skimmed like 3 or 4 papers. I have a friend a colleague rather, who thinks that there's something to this in impacting human behavior. But 30 to 70% of the population infected by this thing. That's just crazy. Of the worldwide population. That's insane. Some worm parasites cause amphipods to move from sheltered areas into areas of bright light, where they're more likely to be seen or eaten by birds. So the hosts complete their life cycle. So, and then one example of that is then the cricket jumping into the water. Okay, we're back down. Okay, sorry. Changes in community structure. A parasite can attack the dominant competitor and suppress the species, causing the other species to increase. In stream communities, the caddisfly was a dominant herbivore before an outbreak of a fungal pathogen. So you could think of this, it's not really applied this way, but you could think of it a bit as the keystone species concept where, well, actually you can. Like, there's a great example of this, which is when sea star wasting disease came out, it killed sea stars. And because of that, there was a measured and concern that with the removal of sea stars, you would have an increased dominance of mussels, the primary prey of sea stars. And with that increase in mussels, you'd have a decrease overall in biodiversity on rocky intertidal reefs. And so back to Payne's Chuck and Sea Star work out on Tatoosh, that removal of sea stars changes the entire ecosystem. And so the same way that sea star wasting disease has impacted our intertidal communities, we can look at the same thing in streams where a caddisfly, which is a dominant herbivore, is then lost due to an outbreak, and that opens up space. This is the caddisfly that opens up space for other species, both algae to live directly, and other grazing insects and filter feeders can also increase. And so when you remove the dominant, either in this case competitor in the system, then the other competitors can come up, or in the case of sea stars and mussels, you remove the dominant predator, in that case the keystone species, then it changes the whole ecosystem. And so in this case of removing the caddisfly, then other rare species increase. And so we have certain organisms that are referred to as ecosystem engineers. The amphipod, Corophinium, it's this little, it's an isopod, I believe, or amphipod. I think it's an amphipod. Let me double. That was a long time ago. Corphidium. I don't remember if it was an isopod or an amphipod. It would be kind of weird if it was an amphipod, but I feel like it was. It seems like an isopod thing. No, amphipod. Okay, it is an amphipod. The difference between an isopod and an amphipod, the one way to remember them, so amphipods are squished this way, well, this way and that way. A potato bug is an isopod. They look like they got run over, right? So they're flat on the ground. So this is the ground, they're flat this way. Isopods are the other way. They're tall and skinny, basically. More like a shrimp, kind of like squished over, where isopods are laterally or ventrally compressed versus laterally compressed. So it's an amphipod. So this amphipod's oh yeah, ecosystem engineer beavers are an example. But this amphipod, it's just amphipod right there. Oh my gosh, shouldn't record lectures so late at night. Okay, the amphipod Corphidium is an ecosystem engineer in tide flats. So we'll take a look at what that means. So what they're doing is they're making these burrows. They're burrow down the mud and create these mud islands. And so here you can see, instead of a completely two-dimensional flat environment, we have all of this three-dimensionality, all these little islands. And what those do is they help hold the structure together. So probably a combination of the type of silt that they're bringing up from the bottom and putting to the top kind of compacts down and creates like a little mud cap. And it also breaks up the flow of water. So it slows the flow of water down and helps trap sediment in this flat beach. After the amphipod's gone, all of those little mud islands wash away and you just see the ripples in the sand. And so here the waves are sloshing back and forth over the beach and effectively pulling more sediment off the beach there. With the loss of Corphidium, the amphipod, you have increased erosion. You've increased sediment move from the beach back out into the offshore. And we can look at that through time, looking at this graph of the Corphidium density. It's thousands per meter squared, so 20,000 of these in a square meter, which is a massive number. The parasite hits, numbers crash to a near zero, and we have a corresponding impact on the physical environment. So here we have a measure of erosion of millimeters, and so this is an overall reduction in the height of the beach, and then the amount of silt. And so what's happening is once they're gone and they're not maintaining these mud mounds, then the waves are washing that silt away and dropping down the overall level of the beach, which is contributing to coastal erosion. And climate change is impacting the distribution of diseases. As water temperature is warm, coral bleaching, coral bleaching is a physiological response to warm waters, but there's also, what's the disease that corals get? My friend studies it, the virus. It's, I'll come with it in a minute here. It's not syphilis, but it's like something like that. I forget what it is. But there's a similar disease in corals. I'm like on now. When animals are stressed, they're more susceptible to diseases. And so as water warms, animals get stressed, they become more susceptible to diseases. And so there's these compounding factors. And mosquitoes and other disease vectors can reproduce more when it's warm, or also expand their habitat, like we'll look at in a second here. So particularly as warming is happening, more southern species can move further north. As winters get less mild, that's typically the limit to species distribution. So this is a look at Leishmaniasis, which is a pretty disgusting disease that causes these skin lesions, these skin sores, and it's and this rat is a reservoir species, so it holds in the parasite. The parasite's is it a trematode or a nematode? It's a protist, so it's a protist disease spread by sand fleas, and then it's also held kind of in a reservoir by this mouse. And so as the mouse is expanding its range and conditions are becoming more favorable, more people could be exposed and at risk to this. And so if we look at the blue areas, these are areas that are not at risk in 2019 but in risk in 2020. The green areas, which is mostly right here, they're at risk in 2009 but not 2020. And the red areas are at risk in 2009 and in 2000, sorry, I said 2020, but 2080. So it's expanding habitat north and south as conditions become more favorable. The vectors for these diseases is expanding. So there's both the organisms that carry the disease are allowed to expand as climate changes, as well as things like temperature stress increase. And when organisms are stressed, they're less likely to fight off both parasites and diseases. And so there's a connection there between changing climate and increased parasitism and increased diseases. That was a long chapter. So that'll wrap it up. Long chapter, lots of gross stuff, pretty interesting. But I swear that was probably twice as long as chapter 12. But we got through that one. So come on back for chapter 14.